the first of our seminars for this program, and I thought it'd be a very good thing to have as it were, a warm-up session, and Phil very kindly agreed to give this seminar. We will normally, when we don't have a workshop, we plan to have a seminar, as I think I've circulated, on Tuesdays and Thursdays at this time, 11:30 to 12:30, which seems a good time slot, and we can continue to discuss over lunch all the ideas that no doubt we'll encounter. So Phil, thank you very much. You're welcome return to the Newton Institute. I remember you here at our previous program just over, 13 years ago on topological, what was it, geometry and topology?
Something like that.
So we look forward to hearing what you have to tell us. Thank you.
So, thank you. So, being the first talk, and it's supposed to be introductory. I didn't quite know everyone's interests and backgrounds. So please, and it's supposed to be introductory and informal, even though I'm in this classroom with the 6,000 lumen projector here. So please interrupt me. I can ramp it up, ramp it down, but I'm trying to be very informal and very physical in some sense. And so please stop me, interrupt me, ask me to define things, tell me to speed up, slow down, or whatever seems good. So I wanted to start with kind of a mathematical or a topological metafact. So Keith asked me to get us in a topological mood, so let me talk topology for a minute. And one thing you learn early in topology is that codimension, in the jargon, codimension 2 is the knotting dimension. So that means when you have a complementary dimension of 2, you can be knotted. So we're all familiar, and it's common in topological fluid dynamics, of having knots in 3 dimensions. So you have a one-dimensional curve can be knotted in 3 dimensions. But in fact, if you take the same picture and put it in a 4th dimension, then it unknots. In the 4th dimension, you can simply unknot that. So there's no knotted closed curves in 4 dimensions. So we also, in mathematics, study knotted 2 spheres in 4 dimensions and other higher codimension 2 objects. But I want to talk about 2 dimensions, and in some sense start with the silly question is, can points, so points are codimension 2 in 1 dimension, because they're dimension 0. So can a collection of points be knotted, right? And what would be the implications of that? Well, obviously, the first answer is no. I mean, they're just sitting there. They're clearly clearly not knotted. There's always a difficulty to feel not knotted. But if they move, in fact, they can be knotted. So that's the theme of the talk, and that's kind of the theme of a lot of 2-dimensional dynamics, is that if you have a collection of points in 2 dimensions that wrap around each other in a sufficiently complicated fashion, it has implications for, if we talk about fluid, the surrounding fluid. All right? And in fact, the implication that's most important in fluid mechanics is growth rate of closed curves. In particular, you get exponential growth of material lines, and this implies that somewhere in the fluid, your deformations are growing exponentially with time, and this has lots of other implications. So I'm going to try to formalize this, and there's a whole theory of this going back to the 30s to Nielsen, and in the 70s to Thurston. It's been developed a lot. And I'm just talking about the special case of points in the plane, but I'll try to tell you a little more about what the general theory is about. So I'm going to show you, in fact, an old movie that goes back to the last time I was here talking, but I think it illustrates the main point very clearly. And so here we have, and you can think of this as fluid stirring, and in fact it is quasi-stationary Stokes flow. It's a numerical simulation. And you have 2, I'll call them stirring protocols, which are the motion of the rods. And let me just be explicit what's going on here. So on the left, we do these guys clockwise, then we do these guys counterclockwise, And on the right, we do these things clockwise and then clockwise. All right? So as you stare at it for a bit, you say, well, at least for Stokes flow, they're energetically the same, but what they do to those material lines is radically different. Right on the left, in fact, I'll show you, you're getting exponential growth. Each complete cycle, it's growing by a factor of about 3. Where on the right, you're actually just getting linear growth of these lines. All right, so these, in some sense, are the two simplest cases of the theory. And you have to be careful. I'm using the word knotted points, but if you think about it too closely, you'll get into trouble because it's not quite right. But what I'm thinking of is these guys as knotted and these guys as not knotted. All right, so these are the two main cases in the theory, and in terms of their implication for the material lines, you have exponential growth and linear growth, and then I'll emphasize that means in the fluid you're getting deformations, right, because the thing is incompressible, so if you have regions that are getting stretched exponentially, they're also getting pressed down exponentially, so actually your deformations are going to infinity exponentially in the fluid. And that's, you know, you can put that to use, as I'll talk about next week. So so we want to try to remember this, and I'll keep kind of referring to it. But these are the two main cases, and I'll try to explain the difference and what's going on and what the implications are. But before I do that, let me just say what the difference between these are, in particular what to notice here. First, as I've talked about already, is the exponential growth. The second thing is what one could call an emergent structure. So, right, as you keep doing this, you keep seeing the same pattern coming back, but elaborated with more and more layers of the dye tracer building up. But you see the same basic heart shape over and over again. And also, there are clearly implications if you're trying to mix a fluid with 3 rods. Clearly, this mixes much better than that, at least for these dye tracers, and at least for this Stokes flow. Yes, so where the knot is we have to, I'll tell you that in a second, we need to go out in time. So we take the points and we trace them in time, and then we see a braid, and then when you have the braids, you can distinguish these two by the nature of their braids, right? So that's kind of the next stage, that's later in the story, or very soon in the story. But let me just show you, Mark is gone. So that was done by Matt Finn a while ago. Mark is here at the workshop, so this is an experiment done by Mark when he was a graduate student, back when I was working with Hassan. So here's, again, this is glycerin, and these are just dye tracers in the glycerin. And we just do the same protocols just to show you that in a real fluid, you get exactly the same structures, exactly the same growth, and exactly kind of the same dynamics. And this is not a coincidence. I mean, there's a theorem which says that this has to happen. All right? And there's the apparatus. So, okay, so he seems to be hidden away. So I'm going to go to the board now. You could turn it off and raise it up. Where'd he go? There he is. He's back in the control room. I feel like the Wizard of Oz out here. Okay. All right, so the first thing is what Steve asked about, is how you describe these two protocols, how you formalize the notion. And again, I'm going to try to avoid mathematical jargon as much as possible, but let me just do the two protocols in time going up. So here time is going up, and this one, remember, we cross them. So these are the motion of the stirrers going up in time. We cross them like this, and then these two cross like that. All right, so that's the left one, and I'll keep calling it pseudo-Anosov. People know what a Anosov diffeomorphism is. There's connections to that. And this one, remember, we did this and this. So we did this, and then we did this. Okay. Now, if If you have a daughter, you recognize this is how you braid her hair, and this is how you don't, right? Because if you try it like this, it comes untangled. And this, it actually stays. And in some sense, that's the exact same physical principle which distinguishes the two stirring protocols. So this is called finite order for reasons which I'll eventually explain to you. All right, so these are a way to describe the two stirring protocols, the motion of the stirrers. And braids form a group. These individual crossings are a generator of the group. And there's a whole formalism, whole basically coordinate system. So you can use braids to give coordinates to stirring protocols. And each of the stirring protocols then can be assigned a type according to the theory that I'll tell you about. And the main dichotomy I keep coming back through is exponential growth versus linear growth. All right, and it's all based on the topology, which I'll try to explain to you in a few minutes. Yeah, so it turns out that, at least in the topological theory, there's nothing in between. There's no polynomial growth. There's just exponential growth, and then there's linear growth. And it's somehow connected to two-dimensional matrices, right? If you have two-dimensional matrices, you either have exponential growth or you get linear growth if your Jordan form has an off-diagonal 1. So it's very hard to get linear growth, but there's no polynomial growth. Right, it's an important point. So somehow polynomial growth doesn't really happen, and partly it's a simple thing is you have repeated addition versus repeated multiplication. So it's kind of hard.
ROCs?
Yeah, so in dimension 3, there's some trickiness going on. And so in dimension 3, you can think about braided tubes. And the experiment's been done. And then you join the top and the bottom. And then you force the fluid through. So as long as the fluid moves transversely through and back, the same theory works because you can just take the return map or the Poincare map on a cross-section. But mathematically, if all you know is that this thing is sitting there in your flow, there's not enough control because 3 dimensions is different because the orbits could wander away and not kind of do what you want. So it's very much a 2-dimensional theory and kind of quasi-2-dimensional theory to make the thing run, all right? Except for the, right, where, as I said, you can think of this as quasi-2-dimensional. Okay, so I want to just draw pictures on the board. This is very elementary, but I have to think of my friends Hassan and Slava Maleshko, who are both gone. But when I first talked about this, Slava was most adamant that you can't say anything about a fluid without solving the equations. I mean, he was, you know, he's Ukrainian. He would pound on the table and say this. And I would say it's just topology. And so I'm going to just draw the picture for you and try to convince you that this exponential growth we saw is strictly topological, right? And all it depends on is that the fluid doesn't tear and that the stirrers, you know, move in the same pattern, right? So it's the topological pattern of the stirrers which determines the growth, not the specifics of the fluid model, all right? So
You need an assumption of continuity.
yes, absolutely. So right, the fluid can't tear.
Yes.
So it is quite true that fluids tear. That's how we drink our coffees. And if the fluid tears, the theory doesn't work anymore. So absolutely, we have to assume that the fluid region is continuous and never rips or tears.
You have no slip condition on the rods.
So the boundary condition doesn't matter on the rods, right? Because if you think about the way these guys, oh, well, I'll show you the picture now. But if you think about this guy wraps around like this, it doesn't really matter how it slips on the boundary as long as it doesn't pass through the stirrers, okay? Yes, you can do potential flow. You can, well, you can do like a 1-parameter family of potential flows. So you can, that's actually a solution. Euler's equation, you can find a harmonic stream function at each instant. And the picture actually won't look like that. It'll be reduced to that, but because it's Euler, there's all this secondary folding that comes up, which I'll tell you about in a moment. So, right, absolutely, you can have slip, no slip boundary conditions. But the important feature you already pointed to is this can't tear, and the fluid can't penetrate the boundaries, right? So those are the physically important. All right, so let me just draw a sequence of pictures. And again, This is for a topologist. If I find an eraser. For a topologist, this is, one's bread and butter. But I was supposed to develop a topological mood, so here we go. I'll just draw some pictures, and I'll just iterate according to this stirring protocol, topologically. And when you see it, it's absolute convincing. It should be absolutely convincing that that it's strictly topological.
In this picture, what is in the picture of the braid?
Yes?
What is exponential about that?
Yeah, so there's nothing exponential about this picture. What's exponential about it is that we think of an arc connecting there to there. And then we propagate it with the flow. And as we propagate it, because it doesn't do this, it does this and this, as we propagate it, it winds more and more and more and more. So you're absolutely right. These are just point motions. The important thing is their implication for the ambient fluid motion, right? And that's the exponential part. Right, absolutely. Okay, so let me just go through the sequence of drawings. And again, this is all, as I said, what we do. So let's just do the stirring protocol pictorially. So remember, the right-hand one first went clockwise. So this goes like this. Oops. I did it wrong. No, I went the my notes are wrong. Okay. No, I'm sorry. I did the wrong arc. Sorry. So I want to think of this connected to the boundary here. Okay. So that's a little clearer. And so then we first do this one in this direction. So the first stir just puts this here. All right. So as I was saying, again, it has to be here. It could have secondary folding, could wrap all over here. But if we shrink it as much as possible, it bangs into that point, and that's that. All right? And now we do the left-hand one. So left-hand one goes in the other direction, like this. Right? And so these guys go like that. So the next stage, we come in from here, we go down here, then we go up there. All right? So that's one iterate, and it's not clear at all. This is going to force exponential growth, but by the time we do the second one, you'll see the complication setting in. So now we do this guy. Let me do it in white again. We do this guy in this direction. So these are the evolutions, the steps of the stirring protocol. So when we do that, then this guy goes around there, around there, around there, and then you see some action starting. Let me just do one more iterate. Come down here, and then you have to keep your wits about you. But then what happens here is this guy wraps around like this. So this guy that came in from here now goes up, around like that, back down like that, around like that, and there. All right, so you can stare at it a while, but that's what happens when you do this guy in this direction. So this guy flips like this, so this loop comes here, this goes around to there. Okay? So this is the topological flavor. Yes?
Does it mean you're developing velocities in the particles in the fluid?
Mm-hmm.
Are the particles in the fluid gaining velocities as you do this, or you just?
Yes, so right. So what I'm thinking of is let's just think about Stokes' flow. So let me think about these as stirs in Stokes' flow. So as I move them, the moving boundary creates a velocity field at each instant. And then the velocity field advects or advances material lines in the complement. So I'm just drawing kind of the simplest topological model of how, just like in the experiment, how this material line would be advected if you have a non-breaking fluid forced by the motion of these stirs.
But then if you have exponential growth in that, then you'll get, do you develop shocks, or what eventually happens in the fluid? Because
Well, the exponential growth is an infinite time, so it's not infinite time. All right, so just think of the experiment, or think of this. So nothing mysterious happens at each step. It's exactly the same as the previous step, right? So flow, you have a biharmonic. Go ahead.
It's not velocity that is growing in any way, it's displacement particles.
But if
When you're
well, but
talking
if
about
you shock at a
stirring,
constant rate, then you're getting a velocity.
Velocity is time periodic.
A velocity is
The velocity field is time periodic, but if you look at the Lagrangian map, right, you look at the advance map here, right, each time you get the advance map. You look at the derivative of the Lagrangian advance map, then its spectrum, the deformations are going to infinity exponentially. So it's just when you go from here to here, you see that, but at each stage, it's exactly the same as the previous one.
It's sort of helpful to think of a die streak.
Yeah, it literally is a die streak, just like the experiment. That was a die
Why
streak.
doesn't it cross?
Why doesn't it cross? Well, because it's a fluid, and fluid doesn't cross the boundary. I mean, we're assuming this is a fluid, and these are rods sitting in the fluid, right? And so when you have a material, you have a die tracer in the fluid doesn't penetrate the boundary, so it's stuck on this side of it. It can't pass through it.
It's kind of a solid boundary that the fluid can't.
Yeah, it's a solid boundary. I mean, there literally, if you remember the experiment, there were steel rods coming down into the
No,
fluid.
I'm talking about the yellow line,
The green line?
the green.
Yeah, the green line is the evected die tracer. So there's the die tracer, there's the die tracer, there's the die tracer, like that. All right?
Can't cross itself because
Oh, it can't cross itself.
of continuity of the velocity field.
Right, so the time evolution of a fluid in math languages is bijective. It's a one-to-one thing. Right? So if this curve doesn't cross itself to start with, it never crosses itself. Because if it crossed itself down here, you could run the thing backwards, think of Stokes' law, it would cross itself back there, which it doesn't.
It's of course a material line. Isn't
It's a material line in the fluid, absolutely. And it's a passively advected material line in the fluid. Absolutely, like Steve said, like a die, just a straight die.
What's the meaning of 3? So you can increase the number of,
Yeah, right, so why 3? Well, because 3 is the simplest case.
yeah,
So when you have 2 stirrers, all you can do is this.
yeah.
When you have 3, then you can do more. If you have more, you can do lot more, right? So this is just the simplest kind of non-trivial case.
The orientation of rotation may be changed.
Yeah, so when you have more, you can do, there's an endless game, right? You have braid on 20 symbols, and you can twist like this, and then you have a harder computational problem. But when Jean-Luc Tifo comes, he'll tell you how to compute these things in milliseconds, right? So he's really good at that. All right, so again, so this is an advected material line, and if this was an Euler flow, if we added inertia, there could be secondary, it was Navier-Stokes, or whatever, there could be secondary folding, but this is kind of the minimum complexity it could have, because as we're saying, you can't kind of cross the die tracer can't cross the boundary. All right, so this is the sense in which it's strictly topological. All right, so the next thing is to try to talk about how you compute the growth rate. So I've already mentioned ways of computing this growth rate. So in terms of a real experiment, you go back to those pictures, which you have to remember. There's kind of a growth rate, and that growth rate, as I said, bounds kind of tells you how the eigenvalues of or how the deformations are growing. Not the deformation. Let me say in math language, the derivative of the Lagrangian map. It's not the deformation, not the symmetric tensor associated with the velocity field. All right, so here's a way you can measure it using matrices. And this again works in general, but the 3 points are the simplest case. All right, so this is I should say, predicting the exponential growth rate. And in fact, it really is a lower bound. So I really should be saying the topological exponential growth rate. And I'll try to formalize that in a little while. So the way you do this is, in fact, you do basically a Markov process with the 2 rods and the spaces between them. So let me draw that and try to explain it. And again, you can formalize all this stuff, but I'm trying to be informal. So I want to do the 2 stirrers stirring processes separately. All right, so the first one is I'm going to do this, and remember this went like that, so that went like that. All right, so this is the image of I1, and this is the image of I2. So let me put primes there. All right, so again, just drawing the schematic topological picture. All right, and so now I think in dynamics language, I think of these as Markov boxes, or I think of them as states in a Markov process. And what is the nature of this Markov process? Let me first just draw the diagram. Is I1 covers itself, and I1 covers I2. And then I2 simply covers itself. Now, it also reverses orientation, but that won't matter. All right, so in the world of Markov processes, what you do is you write down a transition matrix, which tells you how things transition. And traditionally, you use the rows here. So I1 covers itself once. It covers I2 once. I2 doesn't hit I1, but it covers that. All right, so this is a matrix which, for the simplest move, for half the stirring process, encapsulates what happens to these guys. All right, so that is a description of what happens to those simplest material lines. All right, now I want to do the same thing with the other stirring protocol, and then compose them, which will be multiplying the matrices, and that, in fact, will give me my growth rate. All right, so now let's do the other one. All right, so the other one, we rotate in the other direction. So we go in this direction. So this guy is like this, like that, and this is I2 prime, this is I1 prime. So now it's almost the same diagram, but now I1 just covers itself, I2 covers itself and covers I1. And then our transition is 1, 0, 1, 1, like that. All right, so this is 1, you get this.
What do you mean by I1 covers itself? Okay.
Yeah, so what does I1 covers itself mean? So I'm thinking of kind of growth here. And so when I rotate this, then I1 is there on top of where it was originally. All right, so it falls back on what, the idea is we're going to iterate this process. So if I1 falls on I1, the next time under this it falls on I1, but on this it'll fall under I1 and I2. All right, and so that tells me that what I should do is multiply these matrices to do one then the other. So the entire protocol, or the entire cycle, is described by, well, we can do two things with it. Let's multiply the matrices, and hopefully I got them in the right order here. We do this one. Now I have a transpose here, so we're actually doing the other one first. But we do this times this. So we do this times, and then we get 2, 1, 1, 1. Okay, so this describes doing this and then that. All right, so now let me draw yet another picture which shows you, let's do the 2 and just see that this is an accurate description of how we get covering. So once again, let me just start with my picture like this, I1, I2, and then the way we did the protocol, the first stage was like that. And then the second stage, we wrap this around. So this comes to here. This goes like that. This is I2 double prime. And this goes like that. This is I1 double prime. All right, so if I do the protocols, again, first this one goes in this direction. This one goes in this direction. I see that I1, so remember, this gap here I'm calling I1. I1 covers itself 1, 2, right? So I1 covers itself twice. That's this part of the transition. And everyone else, for example, I2 covers itself once. I2 goes across I1 once. All right, and I1 just goes across there. All right, so if I do this, again, heuristic, and again, you can formalize this, but I'm just trying to see how these arcs have to grow, and this is telling me, if each one of these is length 1, how things have to grow. All right, so now the question is, what's the growth rate? Now we know this matrice says that this arc goes across this one twice, and then we repeat the process. We want to know, so what's the length? So the length after n cycles. So what do? Well, you take the matrix, raise it to the nth power, and let's multiply it times some vector v, say. All right, so we want to have some initial vector. Let's say we start with this guy, which would be starting with 1, 0, and then we keep iterating it, and we want to know how long it gets. So in fact, we want to take a norm here. So that's the length of this. For example, a 1 norm. And now the question is, how does this guy grow? So how you iterate a matrix, how the norms grow? Well, it grows like the spectral radius. All right, so again, let me just be rough here. This grows like the spectral radius. This is the spectral radius. To the nth power. All right, if you like, just pass to the Jordan form or use Gelfand's theorem or whatever. So this grows like this, and let me put an initial norm here. All right, so this matrix, as you iterate this matrix, it describes the length at each stage of the material lines, and then we have to figure out the spectral radius. And what it is I think I'm running out of boards. So what is the spectral radius? Let me erase this thing. So this is equal to, let me just write the number here. Well, it's 3 plus the square root of 5 to the n. All right, and whatever that number is, it's at 2.6. All right, so if we actually went into the experiment, so you have to go back and think of those pictures, and we measured the material lines and how long they were after every cycle, in fact, this is exactly right. So Jean-Luc has done this on this experiment many, many times. So you have to do it numerically, of course. It's a little hard experimentally. So you iterate, advected material lines. You compute their length at each stage. You do a log-log plot, see what the exponential growth rate. It's within very close to this. Okay? And again, this has to be a lower bound. This is what I keep telling you, is that it could develop secondary wiggles, but this level of growth has to be there for at least this type of curves all the time. All right? And this number is completely computable. All right? I mean, that's part of the theory. Okay?
Just remind us how you calculate it. Is it from the eigenvalues of that little matrix?
Yeah, so I just computed the eigenvalues of this matrix.
Yeah.
So it's trace plus or minus the square root of trace squared minus 4 times the determinant over 2. So that's the spectral radius.
I can't help remarking that from the diagram, if you simply count the number 1, and then 2, and then 3, and then 1, 2, 3, 4, 5, and then 8, it's the Fibonacci sequence, which has the same.
Right, and that's associated
It
with
must be.
this matrix, right? And what is this, the golden ratio or
Look at this. Yeah.
or the square? Maybe it's the golden ratio, not the square. Right, so this is special because it's 2, 1, 1. This also corresponds to Arnold's cat map, and people know about that, which in a way I'll tell you about if there's time. All right, so in general, there's a general theory now, which I'll try to explain to you, that tells you if you have any stirring protocol, I've already asked, you have more stirrers, and you can take those, describe them as a braid, and then plug it into the machine that's given to you by math, by 20 years of work, 30 years of work, and it spits out linear growth, exponential growth. The exponential growth is this, all right? So this, again, is a lower bound for the exponential growth in a real fluid. For example, if you stirred a real fluid like this, it's finite order, but it's, your coffee gets stirred very well, right? So there's other things going on in a genuine fluid, but this is a topological lower bound.
So you're saying 4 stars or 5 stars is still good?
Yeah, 4 stirs or 5 stirs if you do the right thing, right? If you do 4 stirs, and morally speaking, it's just rotation on a circle, then you're going to see the finite order thing. But if you do this, 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 and this, yeah, then you're going to get some other number and some other computation. The computation turns out to be harder than this because things flop back, etc. But in principle, that's right. Right.
Is there an upper limit to what you can get with increasing numbers of rods?
No. Well, right. So it's a good question. So if all you're measuring is the exponential growth rate, then you have more, well, so here's a dumb answer. Let's say I decide my stirring protocol is to do this 30 times. All right, so then my growth rate is this to the 30th. All right, but if I have more stirrers, then I can make it arbitrarily large. Now, maybe what you're actually asking is, what about efficiency? So you might say,
Yeah,
per stir.
yeah.
Per stir, right. So you want to maximize the efficiency per stir. So right, so that's what Tifo is going to talk about next week. So in fact, you can prove theorems for certain types of protocols. You have to, what you do, right, you take this per unit motion, and you want to optimize that. All right, so it seems to be a hard problem in general, but in special cases, we know the answer. Right, so there is a nice kind of maximum that you can have if you normalize it. So again, another way of thinking about it is, can you maximize stretch per unit expenditure of energy, right? Which is really kind of what you want to do. And there, the answer is somewhat known, but not completely known. Yes?
You are assuming that the 3 points stay there. In other words, you're not moving them around, getting them close. I mean,
so that is the initial assumption that I'm making for simplicity. Right.
I mean, you could imagine them coming together exponentially or something like that, is there?
Yeah, so again, so the region where so you can imagine these 3 moving. But on the other hand, that maybe they're moving nicely in a fixed frame. You can imagine the frame is moving. So, and then if they shrink down, then the arcs that are growing exponentially are disappearing on you, and then your conclusions disappear.
So there is something about the steadiness.
Yeah, there's a scale, right? So,
Scale.
right, there's a scale that's set basically by where these things live, and the fact we stay at that scale, right? And if you start changing the scale, now it's all right to move these around basically and keep the same scale, because basically you just pass to the frame of them, okay?
So
Yeah.
given 3 stirrers, and that is the maximum growth rate.
This is, well, it's not the maximum, this is the maximum growth rate per unit interchange.
Unit interchange.
Yeah, so that you can prove.
So how about configuration of the 3 points? So you assume the straight line.
Yeah, so it doesn't matter so it's all topology, so it doesn't matter where they lie.
Yeah.
It's here, 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 because the braids, it's all the braid. So it doesn't matter where they, so again, this is a topological lower bound. For a real fluid, that really matters, right? I mean, if you do the whole thing in some tiny thing in the middle, well, you get exponential growth in some tiny thing in the middle, which is not what you want. So, right, so there's a real fluid has a real scale, yes.
For more than 3, does it matter which order you take?
Yeah, absolutely. So if you think of, so there's a group, so each interchange is a generator of a group. Every stirring protocol is an element of that group. Every element of that group could be linear, could be exponential, and it turns out there's a case which is a mix between the two in terms of subregions of the fluid do exponential, right. So this is the theorem that I'll tell you is the Thurston theorem. And again, this is a deep theorem that I'm just kind of using a piece of. Okay, so here I think is the answer to some of the questions about more stirs. And in fact, in fluids, you're usually just interested in planar domains, but in fact, the theory was about any homeomorphism of any 2-dimensional surface. So it holds on toruses and multi-hold toruses and all such things. But usually, well, sometimes, but not always, we don't want to do fluid mechanics on a two-hole torus, even though there's sometimes it can be valuable to do that. All right, so let me state this theorem. It's going to have undefined quantities in it, of course, and I will have to decide how to deal with that. You want to give me a hard time, or ask me, not a hard time, sorry, question me about it. All right, so here's the Thurston. So Thurston was in the 70s, and Nielsen was in the 30s. Was interesting thing about Nielsen, if anyone is from Denmark, is even though he was a topologist, part of his job was teaching mechanics. So the mechanics book that was used in Denmark for 30, 40 years was written by Nielsen, who actually was a topologist by training, because that was part of his job, was teaching. As everyone does these days, we have to teach engineers. All right, so here's the Thurston-Nielsen theorem. And again, I'll specify. So let beta be a stirring protocol. So that just means a motion of the stirrers. And because Steve asked me, it's periodic, right, to make the theory. And it can be on n bigger than equal to 3 stirrers. All right, so the theorem is kind of still true, but it's trivial. All right, then either, so this is the dichotomy. In fact, it's trichotomy. And let me push this up. So there are 2 main cases. And this is, as I said, all computable. So the first thing is that beta is of pseudo-Anosov type. And there exists a lambda bigger than 1. That's called the dilatation. Or sometimes just the stretch rate. And a constant C1 bigger than 0. So that, and now here, I'm going to have to slip in something I'll define for you in a minute, so that for all essential gamma, so gamma is a material line or an arc, that the length, and again, we can't really do the length, we have to do the topological length. Well, actually, we can do the length here. The length of beta to the n of gamma. All right, so what that means is beta to the n means we do the protocol n times, and we apply it to gamma. So we advect for n periods, for n cycles of the stirring protocol, the passively advect the material line gamma. So this length is bigger than or equal to the constant C1 times lambda to the n. And then, just to be careful here, I need to start with the length of gamma just to normalize the thing. All right, so that's the exponential growth rate. So if beta can be determined to be pseudo-Anosov type, and this is algorithmically possible, so there's whatever it is, I think it's a polynomial time algorithm, which takes the braid and computes this for you. And it also computes a matrix. It's a little more complicated than this, but it computes a matrix, and the spectral radius of that matrix is the growth rate of the iteration of the matrix, and that's what this lambda is. All right, so this is the exponential growth rate, and as I said, the simplest case is sitting up there on 3 things. All right, so the second possibility is that beta is a finite order type. And now I will have to say something because we're going to have an upper bound on the growth, but it's just the topological growth, so this I'll have to define for you. Then there exists a C2 constant bigger than 0 with, and now I have to tell you what the topological length is. So let me just call it we don't have to be real for it. The topological length of beta to the n of gamma is less than or equal to Cn times n, so this is the linear growth, times, again, I have to normalize this with the topological length of gamma. C2, right, sorry. Yes. So this constant is just, the constant depends just on the protocol. It's not universal. All right, so this again is this guy here, where we saw things grew at most linearly, and the constant was there. And then the last case doesn't happen with 3 stirs, but certainly can happen with more. Or the third case is beta is what's called reducible. Combining pieces from 1 and 2. All right, so any protocol on 3 or more stirs, and again, there's a big machine you can plug this into. It's not a simple machine, but it's well established. You can plug it into, you give it the protocol, it spits out either this was pseudo-Anosov, here's lambda, or this was finite order, or this is reducible, and in fact, it also will tell you what the pieces are. Okay, so there's freeware out there which does this for you. It's based on what Thurston did, and also a lot of people since then. It could grow exponentially or not exponentially, depending on what the pieces are. Right? So when I say combining from 1 or 2, if it doesn't have anything from 1, then it'll strictly be linear. All right, so the growth rate will be the supremum of these components. All right? So it could have lots of these. So let me first.
Can you just tell us what the difference between length and topological length is?
I will tell you that, but first let me draw a picture of reducible. Hopefully it's clear. And then I'll explain what I mean by the topological length. All right, so let me just draw a reducible braid here, and it should make it clear what's going on. So I'm going to have 9 strands. And so the 9 strands are all collectively doing what the 3 strands did. Right? And this would, if I left it like this and connected it up, then we'd be in a case where we have 2 components of this type. But if I decide to say, at the last minute or at the first minute, depending on how we do it, we're going to do this, then we think about this, we have this tube. And another way of saying this is we have our stirs here, 1, 2, 3. Each one has 3 substirs, which are the real stirs. These go nicely like this, but these 3 get wiggled up when you go on. So this is what reducible means. So you can imagine drawing pictures like this. So basically, if you know knot theory, these are like satellite knots. All right. So the 3 stirs are like a satellite orbiting around the finite order thing. All right. And again, time is going up here. Okay, so that's the reducible case. And again, this is all computable and understood and all such thing. So now let me talk about topological growth. Yes?
For one,
Yes?
this is exponential is a lower bound.
Lower bound, yeah.
Optimal, or sometimes we find super exponential.
Yes, so it is true that this is a lower bound. And it is true that there is, no problem. It is true that there is a particular fluid which realizes this. All right. So by particular fluid, I mean you need body forces, right? So there's some in math language, there's some diffeomorphism which realizes this, some abstract area-preserving family. Whether you can actually realize that by Stokes flow is another issue. All right. Now, that's the lower bound, and above it, well, you think you can't. So material lengths can't grow super exponentially in a fluid because it just can't happen, right? Your eigenvalues grow at most linearly as the thing evolves. And so it exponentiates, so you just can't grow super linearly in a fluid. I mean, because it's like iterating, because, I mean, you have the tangent, well, I don't know what you would call it, you have the tangent map of the Lagrangian thing. It's a matrix, and you iterate matrices. You know, the spectrum can't grow faster than exponential.
The kinematic statement.
That's a kinematic statement, yeah. So that's strictly, it has nothing to do with fluids. This has to do with one, in my jargon, one parameter family of diffeomorphisms, right? Yeah, so right, strictly kinematic, nothing to do with, you know, restrictions of the forces or anything. Yes?
You can have the 3 large stars nodding.
Right.
And you can have the sets of 3 also nodding.
Yeah, you could do both, right? I could say, okay, I could do this.
You say that still gives you only exponential growth. It's not
No, yeah, it gives you,
years.
yeah, no, it'll give you exponential growth. It won't, you know, this and this. So you'll get this one kind of on top of this. But if you think about this one, it takes 3 iterates to see this one, right? So the actual growth rate is something like this growth rate to the 1/3 power times this growth rate, something like that. Right, but you can, right, if you take the supremum, you actually get the 1. Okay, anything else? All right, so let me talk about what topological growth is and what topological length is, because that's the heart of the lower bound, and that's the heart of kind of the topological side of it. So let me first draw a picture and then try to formalize it. And let me move my holes to a different place. So here, so let's put them here, and let me put more in here. So these are material, these are blocks in the fluid, right? They're obstructions. And then I have some curve that is, say, I don't know, does what? Like that, all right? So this, again, you should think of this as just a material line, a dye tracer in the fluid. Now, topologically, it's got a bunch of secondary stuff going on that's kind of geometric, I would say, in character, and not topological. All right, so what do we do is I want to choose the shortest curve that has the same topology. All right, so in topology language, I'm passing to the homotopy class of this guy. Or in geometry language, I want to pass to a geodesic. So I put a Riemannian, I put a metric here, then I pass to a geodesic, which is the shortest curve that traces this. All right, so again, if I thought about what that was, and I had kind of the standard metric, it would be that, and maybe that, and maybe that, and maybe that, maybe that, maybe that, maybe that. Oh, I went around the wrong side of it. Thank you. Okay, so the first point, so this is like Cauchy's theorem, right? So Cauchy's theorem say if you deform a curve, you get the same integral. It's the same thing, homotopy. So these two guys, there's a continuous family of curves or material lines which deforms this one into this one whilst keeping things on the boundary. Okay.
With a piece of elastic.
Yeah, so think of it exactly like it's a piece of elastic. So you take this guy and you did something strange to it, then you let it go, and boing, it goes down to its shortest length. Right? It's just like a geodesic, if you know. And so, again, without formalizing all this stuff, so the length topological of gamma equals the real live length of gamma hat, right, where the colors indicate what it is. Okay? So when we do this theorem, it says that, again, just if you have 3 stirs in your coffee, it stirs the cream really well. It mixes, and you'll see exponential growth of derivatives. You'll see eigenvalues of the derivative of the Lagrange evolution growing exponentially in places. But it's not topological in this sense. So we do the stirring protocol, we shrink to the shortest length, and then compute this thing. We do it again, compute this thing. And it's saying that this growth has this upper bound, right? Which is different. You know, if I didn't have this, then it's obviously false. Okay. All right, so that's the topological growth. And of course,
And that would be very different on a sphere.
yes, on a sphere, right, on a sphere, you can also have holes on a sphere. Right, if you stir things on a sphere, then things are okay. It's pretty much the same, but the problem is now this curve has become the same point. So you have to worry about slipping around infinity. And then if you're worried, right, if you change the metric, you get a different number, but that actually washes out when you compute at least exponential growth. Okay, so let me see what other remarks. It's till 12:30. All right. Okay. So first, as I said, this Thurston-Nielsen thing is quite general. You have any surface, and you can have a surface. You can have holes in the surface, and you have transformations of the surface, and the theory applies to it. And that's where context it was really proved. The thing I haven't talked about is the emergent structure. If you go back, maybe I can do this quickly. Could we turn the back on? Is he back there? Oh, cool. All right, it's probably a good way to end this up with looking back now. Hopefully I've explained all this in detail, and then we can look again at the experiment and compare it to what I told you, and you'll see, the material growth and how it's independent of the actual fluid model and the linear versus the other one, and the importance of the topological growth as compared to the other one. All right, so again, it happens, and because this guy, it's because it's Stokes flow. Because it's Stokes flow, you're not seeing anything but linear growth. You're really seeing the topological growth rate. But as I said, which Matt has done, if you simulate an Euler flow with this, or potential flow, a one-parameter family of harmonic stream functions, then you do get exponential growth in some places. So it has to do with Stokes flow minimizes the deformation tensor, right? So there's the Stokes flow kind of does as little as it can, so it has to do with, at each time it minimizes the L1 norm of the deformation tensor. All right, so here you see this guy keeps wrapping up. It's growing exponentially. Things are increasing by length 3 at each stage. And so at the end, after, let me go on to the next thing. So these are the dye tracers in the fluid, and these are physical rods, and then the dye is just advecting there. So after 9 iterates, or did this computation, after 9 iterates, on the left, the material lines have grown in length by 5,620. All right, so when you get here, again, if you take those matrices, figure it out, raise it to the 9th power, you see that the material lines, of course, they've lost, diffusion has taken over, but they've lost their integrity. But by the time you're here, lengths have grown by over 5,000. All right, so and there's the apparatus. Let me tell you very quickly about this emergent structure. And so sorry if this is really fast. So hopefully people know about toral automorphisms. If you've taken a dynamical systems theory, you know about toral automorphisms. So you take a map on the plane, like 2, 1, 1, 1. It preserves it's doubly periodic, preserves the integer lattice. So it gives a map of the torus, which is one of the standard models of chaos. All right, and you have these Lyapunov exponents, which measure the growth rate. And this is the Anosov in pseudo-Anosov. Okay, so let me show you a picture of what an Anosov does. So here, this is an Anosov on the torus. So this is just a map on the torus. It turns out to be incompressible. It does preserve the area. And we start with just half the torus, and we iterate, and very quickly it mixes like crazy, and things stretch like, in fact, the same thing, the eigenvalue of 2, 1, 1, 1. And the thing to notice here is that you are approaching what's mathematically a foliation, but this guy is stretching, and in fact, it's getting closer and closer to an irrational direction. All right, so this is what an Anosov map of the torus does. Now, it turns out that our map of the disk is closely related to this. And again, I'm sorry this is a little fast. But so it turns out, so this again, this is serious topology. So this gives you real flavor. But if you take the torus and flip it and map it to itself, and then you identify points, then in fact, this is like the Weierstrass P function. You get a sphere. And when you have the Anosov acting on the thing, sorry, this is so fast, I'll just show you a picture in a second, it descends to an action here. And so, this is what I told you already. So here's the story I want you to see. So on the plane, when you act by 2, 1, 1, 1, you have an unstable eigenvector and a stable eigenvector. And if you take any blob and iterate it, it finds this unstable eigenvector. And if you take this unstable eigenvector and send it down to the plane, you get exactly the structure we saw before. So if you have, let's go back to this picture. So kind of the thing is, you take anything on the torus, you hit it with this map, it's going to find this wrapping, this direction, this foliation, right? And then, yes?
Are those all torus knots?
Hmm?
Are these torus knots?
Yeah, so they turn out to be torus knots on the torus. That is correct. I mean, the image of this, well, yeah, the image of this is a torus knot. Yeah, right, because it's, yeah, right, it's a finite, it's a rational wrapping. But it's converging to an irrational wrapping, which is not a torus knot. All right, so here it's just the comparison. So this is what happens when you do the thing on the torus and project it down, and that's what's happening in the fluid. So this is exactly the story, and what this emergent structure is that you're seeing is, mathematically speaking, it's the unstable eigenvalue that you're seeing also with the 211, the Anosov. So this Anosov is connected, as I said, to linear Anosov, and I think that's probably a safe, good place to stop. Okay, thank you very much.
Thank you very much, Phil. That is a wonderful foretaste for us. Very, very interesting stuff. Conrad.
Now, if you have these three stirrers, and the protocol of swapping is
Right.
random, you
Right, so you
which
choose,
pair you decide randomly whether it's going to be clockwise swap or anti-clockwise swap.
yes, right.
What happens then?
What happens? Okay. So again, wonderful question that in fact Jean-Luc and I are working on. So this, in the math jargon, this is a random walk on the braid group. So you make a choice, this generator, this inverse, this, and then you march like that. So I can tell you what it is numerically and what, so numerically speaking, you have to normalize, basically you converge to this thing, right? So if you do this randomly, then what you see basically is kind of this growth rate emerging with again, this isn't a theorem, with probability 1. So it turns out, and again, Jean-Luc is the one who's done all the numerics, if you take like 5 braids and just randomly choose a protocol, then it turns out that almost all the time you get exponential growth. It's very hard to organize this thing so it doesn't have exponential growth. And if you do them at random, in fact, it isn't better, right? So it turns out doing this, then this, this, then this is the absolute most stretching per unit switch. Can't do any better by randomness, right? Right. So the kind of the deterministic choice is the best, right? You can't get better per unit, per unit.
And you get numerically the same rates of golden mean?
Yeah, so numerically, again, you have to normalize this thing. So you do these random, so you pick a material line, bang it with this protocol made randomly for n steps, take the nth root of the growth rate, right, and keep doing this, and then do this for a big sample of random things. And of course, you get a bell-shaped curve, but the center of the bell-shaped curve is this guy. Right, so this, and there's a special thing about 3 stirs. 4 stirs is much, much harder, and it's a whole different ballgame. But, and the reason for it is it's connected to these toral maps, so it's connected to a matrix group, and then it's all kind of doable. So there's
4
some
stirs, you're into a 3x3 matrix, are you, for the...
Yeah, 4 stirs, you're in a 3x3 matrix, or perhaps 4x4 because of some other things, right? And then, right, then more can happen. Right? There's not a close connection to a matrix group.
For a given protocol,
Yes.
is it easy to distinguish case 1 and case 2 without doing all the work?
Well, I don't know what you mean by the work. So you can, I mean,
In other words,
you can do the, well, you can do an experiment. That may be doing the work. B is you can draw a picture and stare at it. And if you're a topologist, you can say, you see, it turns out there's an old theorem that, so finite order means that after some iterate, it comes back to itself. So this is an old theorem due to Sam Eilenberg. So it turns out the only finite order one is topologically this, just rigid rotation, right? And so if you can stare at it and see that, again, the work means what's your background. You look at the picture and you can see that, then you're done.
No, it'd just be the unknot, right? No.
Or it could, of course, go straight down. Or part of the deal is,
Rate would be the unknot, is everything knotted should give the exponential growth.
that's right. But if it's an unknot like this, the kind of point is that because we're allowing slip boundary conditions, if it just rotates like this, then you can just unrotate it, right? So if it's just spinning like that, so that's kind of the finite order
I
case.
suppose you can recognize it from the matrix that you get.
Right, if you compute the matrix, and you can, the eigenvalues in the matrix are either off the unit circle or on it. If they're on it, it's finite order. If it's off, but that's kind of work you have to do.
for example, is it possible to have clockwise and counterclockwise, at least one of each, and not have case 1?
No, I believe. So again, there's theorems. There's theorems that say on 3 protocols, if you have these, you know, there's it's a big industry, right? If you have this, then you have this, you have this, or whatever. Yeah.
Yes, Yoshi.
Oh, yeah. So about the toral
Yes.
map, the final set of limiting set is always ergodic.
Yes, so for the actual toral automorphism, it preserves the Lebesgue measure, and it's ergodic,
Ergodic.
right? And then when you push it down, it's ergodic with respect to the Lebesgue measure. In fact, Bernoulli, if you know what that means. So it's very strongly mixing. It's strong mixing Bernoulli. But that's a specific map.
Yeah.
You don't know that if you stir a real fluid and it's Stokes fluid, you actually get that. But that's kind of a lower bound. Again, there's another part of the theory that says that
Fine.
the measure, that ergodic measure actually persists in the fluid. So there's some ergodic measure that remembers that. But unfortunately, it could be supported on a set of 0 Lebesgue measure. So it's kind of morally there, but it doesn't give you global mixing in the mathematical sense. Anyone's from Europe, they're very hungry now. Yes.
Is there kind of behind the scene that the complement to those braids is has either hyperbolic metric or Euclidean metric?
Absolutely. So if you take the braid and close it and put in the braid axis, it's pseudo-Nassau if and only if it's a hyperbolic 3 manifold. Right.
And that's
Exactly
the
right.
reason for the linear growth in particular. That this
So the linear growth is because it's an iterated toral knot, right? So it's not obvious, but it is true, right? So the hyperbolic structure on that 3 manifold is connected to the exponential growth, right? You know hyperbolicity is always associated with exponentiality. Yeah, so again, if you think of this in 3 dimensions, it's connected to another piece of Thurston's work.
Very good. Well, I think we wind it up there. Thank you again.
Appropriate place.